Okay, hello everyone. So in this video, we are going to be looking at an extension of this formula here on the screen, which gives us a neat way to calculate the Laplace transform of the derivative of a function, just in terms of the Laplace transform of that function. So it's a natural question to ask, do we have, for instance, a similar formula for the second derivative or the third derivative and so on? And the answer to this is yes, and here's the formula. So given a function f, which has n derivatives, and the derivatives up to the n-1th derivative are all of exponential order, then we can calculate the Laplace transform of the nth derivative just according to this formula here. So this looks like quite a complicated formula, but actually it's quite simple. Well, it's a simple extension just because the way you get this formula is just by repeatedly applying the first order formula. And then this formula is really just that, what you get from doing that. Okay, so one question you may be asking is this condition here that all of the derivatives are of exponential order. So is it really necessary? Could we, for instance, have the same statement but without the first and second all the way up to the n-1th derivative being of exponential order? In other words, let's ask the question, if a function has exponential order, does it necessarily mean that its derivative has exponential order? So the answer to that is sadly a no. And the way to see this is we can just take a look at this counter example here. So we take the function f of t equal to sine of e to the t squared. And then the reason why we choose this function is because when you graph it, you can actually see that as t increases, it gets much more jaggedy. And that's just really going to give us that the derivative is going to increase very fast, more than exponential. So if you take the derivative of this function, you'll be able to see that that's not of exponential order, and I'll leave that to you. Okay, so we really do need these conditions, that the first, second, and all the way up to n-1th derivatives are all of exponential order. Okay, so we have this formula, and let's just apply this formula in a practical, useful way. Let's try and solve an initial value problem. So we're going to go to an initial value problem here. So it's just this one. So we saw in the previous video how to solve a very simple example. Let's try a slightly more complicated example here. So we're going to, the method is really just going to be the same. What we're going to do is apply the Laplace transform to the left and to the right. And of course, they have to be equal. And then we're going to solve for what the Laplace transform of y is, using the formula for the higher order derivatives of the Laplace transform here and here. And then we'll be able to reason, using a partial fraction decomposition, what the inverse Laplace transform of that function involving a should be. Okay, let's get straight into it. So if I take the Laplace transform here of, so starting from this equation here, I will get that this Laplace transform, so whatever y is, the only thing that I know is that if I take the Laplace transform of this, I should get the Laplace transform of cos of t times -2. Why times -2? Well, just because if I take the Laplace transform of -2 times cos t, then because, as we've seen before, the Laplace transform is linear, the -2 can come out. So I just did that in one step. Okay. So here, at this point, what we're really going to do is just apply general formulas and principles and try and solve for the Laplace transform of y. So using linearity, on the left here, we're just going to get Laplace transform of y double prime minus 2 times Laplace transform of y prime plus Laplace transform of y is equal to -2. So -2 times the Laplace transform of cos of t. So how do we know what that is? Well, we have this table. So this table is really going to be a very helpful thing for us. It's going to be like a toolbox for helping us solve these kinds of problems. So in this case, cos of k times t is given by this formula here, s over s squared plus k squared. And so we just see that if I want to take just cos of t, it's case k equal to 1. So I just get s squared plus 1, because 1 squared is 1. Okay, good. So at this point, the only thing I have to do is apply my higher order formula to these terms of here and here to get to extract out this Laplace transform of y. So let's do that. So applying this, so using our formula that we saw in the beginning of the video, this Laplace transform of the second derivative is just going to be s squared times the Laplace transform of y minus s times y of 0. So I'll just put that as y of 0 here. Minus y prime of 0. Okay, so just using our straightforward formula from the beginning of this, we can actually just quickly go back up to it. So that's this formula over here. So in the case n equal to 2, we were just using this formula to get this formula over here. Okay, so then, great. So we've done that for the second derivative. Then in the first derivative case, we're just going to have, let's see here, what will it be? It will be s times the Laplace transform of y minus y of 0. And then we add that to the Laplace transform of y. And all of this must be equal to -2 times s over s squared plus 1. So that's good. And at this point, our goal is always to just solve for the Laplace transform of y. So there's a lot of simplification that one can do here. So we're going to collect all of the Laplace transform terms and factor out whatever we can. And what we'll get is the s squared minus 2s, let's see here, plus 1. So I'm just factoring out the L of y as much as I can. And then minus s minus 1 equals -2 here. -2 over, so nothing changes on the right-hand side. -2s over s squared plus 1. Okay, so this is where we are. We're still looking for Laplace transform of y here. So we just take this term over, and we just get, by the way, this s squared minus 2s plus 1 can be simplified. It's just s minus 1 squared, right? Great, then I take the s minus 1 over, and I just get here s plus 1 minus 2 times s over s squared plus 1. And great, now I have my my formula for the Laplace transform of y. The Laplace transform of y here is just going to be given by, okay, -2. Let me do it. So s plus 1 here, divided by s minus 1 squared. It's just dividing through by the s minus 1 squared, minus 2 times, just s over s minus 1 squared times s squared plus 1. Okay. Okay, great. So this is a fairly complicated looking expression, but you'll be able to simplify this. So one can always do a partial fraction decomposition here. So the denominator, whenever you're given a ratio of two polynomials, you'll always be able to write that as a linear combination of simpler combinations, just simpler rational polynomials, just using rational functions, just using partial fraction decomposition. So you'll get squares at most at the bottom in this case. So here we'll just get 1 over s squared plus 1 plus 1 over s minus 1 plus 1 over s minus 1 squared. Okay, so there is a lot of work to get from here. You're probably wondering, how did we get here? Well, the simplest way to check that is just to add these two together and check that you get this. But otherwise, the way we get this is just by using a standard partial fraction decomposition. Okay, so why are we looking for functions in this form here? The only reason is because we want these functions to be of the form that we can see on the right-hand side of this table. And why do we want that? Because if we can do that, then we can apply the inverse Laplace transform and solve for what is y. And that's exactly what we're going to do here. So let's just make the following argument, that the function y, which is what we're looking for, of course, is just equal to the inverse Laplace transform of L of y. So inverse Laplace transform of the Laplace transform of y is just equal to y by definition. And so we just get this is equal to the inverse Laplace transform of y, 1 over s squared plus 1 plus 1 over s minus 1 plus 1 over s minus 1 squared. Great. And now inverse Laplace transform is a linear function, which means that the way that I can calculate this expression, let me just actually write that out. So this will actually just be equal to the inverse Laplace transform of 1 over s squared plus 1 plus the inverse Laplace transform of 1 over s minus 1 plus inverse Laplace transform of 1 over s minus 1 squared. Great. That's just saying that the inverse Laplace transform is linear. Okay, so now, great. Now it becomes clear why we were doing all these partial fractions decompositions, because the inverse Laplace transform of 1 over s squared plus 1, well, it's going to be directly of this form here. Okay, we're going to get exactly sine of t if we look at this. So this will give us exactly sine of t, just because the Laplace transform of sine of t will be 1 over s squared plus 1. So the inverse Laplace transform of 1 over s squared plus 1 is just going to be sine of t. And very similarly, here, this function here comes directly from the exponential function given up here, just in the case alpha equal to 1. And similarly, if we take the s minus 1 squared here, if we look at this term here, well, we can actually write that as a function of this. It will be of this form. It will be 1 factorial over s minus 1 to the 1 plus 1. So we'll just have a t, e, t. Great. So just summarizing what we just said, we get here sine of t plus e to the t plus t e to the t. And that's how we can use Laplace transform to solve initial value problems. Okay. So that just about does it for our videos on Laplace transforms. In the future, we move on to other topics. But the general principle is here is that we have, using the Laplace transform, we have a very universal method, a canonical method for solving initial value problems just using this technique here. Okay, thank you.